Hello everyone. So this is our seventh question. It is from Wonder Wall equation of state. So if we rewrite this equation, so this will become p plus a by v square into v minus v is equal to rt. So this is our Wonder Wall's equation of state. For this is direct result. So we remember it like this. So take del P by del V at constant temperature, del P by del T at constant pressure, then uh, then del T by del T by del P at constant volume. So these three product of these three will be equal to minus 1. So we write del P by del V at constant temperature into del P by del T at constant pressure into del T by del P at constant volume. So this is minus 1. So just cross check, this is same, this is same, and this is same. What happens sometimes using some Maxwell relation TSPV. So using this also you can, like, they can change some parameter here and you can place directly from it. So this value will change from minus 1 to 1, like it can be plus 1 also. It depends on the question. So this question is the based on the Dalton's law of partial pressure. So what is given? We have some rigid tank. Okay, it state one. So initially we have its pressure is 1 bar and temperature is 300 Kelvin. Okay. Now number of moles of O2 is 5. Number of moles of N2 is 4. Number of moles of S2 is 3 moles. Okay. So it state to what happens, only the 2 moles of this oxygen is removed. Okay, so 2 moles removed, so 3 moles of N2 will be remaining. Okay, and all other keeping the temperature constant, and nothing has been said about this N2 and S2, so we will consider these moles as same. Okay, so temperature is same. So temperature is same, so something should vary from process 1 to 1 because the number of moles of O2 has been reduced. So the pressure applied by these three here will be less because here number of moles are actually 5, 4, 9, 3, 12 moles, and here 10 moles. Okay, so obviously the pressure will reduce because the number of moles is reduced now. So we have to find the final partial pressure of oxygen. So for that we should know what is the final total pressure. Only then by using Dalton's law of partial pressure we can uh, find the individual partial pressures of gases. Okay, so now how can we write? So using ideal gas equation, because we can assume ideal gas behavior. It is written already in question. So it is state one. If we apply, so see, you can apply ideal gas equation to individual gases also, and to the mixture of gases as a whole, because that is also an ideal gas. So I'm applying to total means assuming all the mixture of ideal gases as one, and mixture of ideal gases is as another ideal gas. Why? Because we will see V1 equal to NT1, total number of moles at stage 1, R bar T1. This formula you know, PV equal to MRT or equal to NR bar T. Okay. Here this is universal gas constant, this is characteristic gas constant. So if we write M as R bar by M, so mass divided by molar mass will become number of moles. Okay. Now at second stage, if I write PT2 total pressure at stage 2 is equal to into V2 is equal to total moles at stage 2 R bar T2. Now see, T1 and T2 are same. If we divide these two, see, so this will cancel out, and here rigid tank is mentioned. So V1 V2 will be same, R bar cancelled, and only this one will remain, PT1 equal to PT2. If I write it like this, 1 divided by 2 is equal to NT1 by NT2. So this known, this known, this known, only PT2 is remaining. So we can write PT2 as this. Okay. So T2 is number of moles in second. Total number of moles are 3, 4, 7, 3, 10. 10 moles and initial 12 moles into what is total pressure. Here we should write in kilopascal. So 1 bar means 10 to the power 5 Pascal. Okay, so we can write it like this, 100 kilopascal. Okay, so okay, now this will be equal to 4 3 is 4 25 to 250 by 3 kilopascal. Let's not convert that into integer, like let it be in fraction only. Okay, now writing what we have to find out, partial pressure of oxygen. So let's find out partial pressure of all the gases. So using Dalton's law of partial pressure, Dalton's law of partial pressure, what we'll get, partial pressure of O2, this at final stage. Okay, I'm not like writing it. Okay, mole fraction of oxygen in final stage into total pressure at stage 2. What is the mole fraction of O2? Number of moles of O2 divided by total number of moles. Total number of moles is 10, and 250 is this, 250 by 3. Okay, see, 3 cancel. This is 25 kilopascal. If we want to find out partial pressure of nitrogen, so mole fraction of nitrogen into PT2. What is the mole fraction? 4. 4 divided by 10 into 250 by 3. So 100 by 3 kilopascal. And for hydrogen, it will be mole fraction of hydrogen at SO2 into PT2. So this is hydrogen, how many moles? 3. 3 by 10 into 250 by 3. So again 25 kilopascal. So for oxygen it is 25 kilopascal. This is the answer. So this is our question 9. This is basically purely based on first law of thermodynamics. So here what we have been given. So we have insulated container. Okay. So no heat transfer, and there is stirrer. Stirrer is there. So which is rotating and doing some work. Okay. So here we have that liquid, 10 gram of liquid. Okay, so during stirring process, what is happening? Energy is transferred to the molecules of liquid here, which is used in raising the temperature of that liquid water by 5 Kelvin. So the heat transferred to the water. So basically, the shaft is doing the work. Like the is has been work is transferred across the boundary here, not the heat, because the container is already uh, insulated. So the heat transfer is zero here. Only the work transfer is there, and that work transfer we can calculate using. So we have already solved the question. The amount of heat transfer to the water, this is zero. But if we want to calculate the heat transfer, we can calculate heat transfer using first law, du plus delta W. Here it is zero. Work transfer minus du. What is minus indicating? Our system is this. Negative sign shows that uh, the work is done on the system, not by the system. So mCp dt. mc dt. For liquid we can write m is 4 point sorry 10 gram into 4.2 into dt is 5 kelvin. So if we check the units, m is in gram, c in joule per gram kelvin into kelvin. So it will give in joule what has been asked. Okay, so it will simply give, this is 42 into 5 and minus 2102. So minus indicates here work is done on the system. This is the work and the heat is 0. So this question is based on the pure substances. So note that here uh, we have to find the work done. It is very important to note that, to think in a think in a direction what has been asked. So work done, we have to calculate work done here. So for, like, let's say for ideal gas we can simply write H is equal to CPDT, okay, and U is equal to CVDT. But here for pure substances we cannot write it like that. Here we have to see for the steam table what is the enthalpy and internal energy. So using enthalpy and internal energy, using first law and TDS relations, we can calculate the enthalpy, like the work done. Okay, but here as you see the data, you can see pressure and volume is given. Okay, so if uh, using pressure and volume, we can simply plot the process in our PV diagram. And if once the we have drawn the process in PV diagram, area under the curve will simply give us that work done. Okay, so let's calculate P, pressure and volume in at both states. Okay, so here M is 2 kg, wet steam is there. That's why wet steam means some part is liquid and some part is gas. Quality this much. So if I try to calculate at 90 degrees Celsius, what is pressure? P1 is 70 kilopascal. And why it is P saturation? Because the situation is like this. It's here quality at point 1. Here uh, this should not be point 1. Ah, sorry. Okay, let it be. So here the quality is zero point 0.1. If I see here, quality is around zero point 0.5. Here zero point 0.9. Okay, here to here quality increases. Okay, so our quality is zero point 0.1. So using this quality, can we calculate our V1? Yes, we can calculate. If we calculate the specific volume V1, V1 will be VF plus X VFG. Okay, so and Vf plus x1 Vg minus Vf. So at 70 kilopascal we have Vf and Vg given. If we put it there, Vf is just 0.0001 double zero 1, Vg is 2.4 meter cube per kg, x1 is zero point 0.1. So we'll get V1 as, I have calculated already, 2409 meter cube per kg. Okay. Now the second at second stage, if we see the pressure is somewhere around very high, like 250 degrees Celsius, and pressure is 800 kilopascal. So 800 kilopascal and a specific volume we have directly given. So it may be in around here, like in superheated state. Okay, so we have been given directly this now. So this is P1 V1 and P2 V2. But you should note here that we have not calculated the capital V1. Capital V1 means directly volume, not the specific volume. You can calculate by directly multiplying by mass. Mass here is this much. Okay. So let's see what is the process here. And also note that here the piston cylinder arrangement is there. Okay. So it is like that. Here wet steam is there. Okay, So see, as the pressure increases from here to here, and here we have spring. Piston is loaded with linear spring. So linear spring means pressure increases linearly. In this case, if it is not linear spring. Linear spring means force is equal to kx, x to the power of 1. Okay. If it follows some expansion x to the power of 1.2 or kx square, it will follow that for like x square this will be the case. Okay. So since it is linear spring, so we can easily calculate now. Okay. Now see. So pressure increases from where to where? It increased from 70 kilopascal. It is PV curve, 70 kilopascal to 800 kilopascal. Okay. Now the volume we know. Here we have, let's mark it as V, but let it be V. So here we have V1, here we have V2. So area under this curve will give us the work done on the spring. Okay, as the pressure increases, so spring uh, it will move upwards. So spring will compress. Okay, and that will be stored in the spring. That work done by the system on the spring will be stored in the spring in the form of spring energy. Okay, half kx square. So we will calculate now work done. Half area of trapezium is half sum of parallel sides, into base. Parallel side is one is 70 plus 800. These are two parallel sides, so sum of these two, and into base. Base is V2 minus V1, and note that it is 870, and V2 minus V1 we can write as m into a small v2 minus a small v1. Okay, a small m is 2 into v2. V2 is 0.29 and v1 is 0.2409. And if we calculate this, we'll get 42.717 kilojoule. Okay, units are also correct. You can cross check the unit. So its unit is kilopascal into it is m into v2 minus v1 meter cube per kg. So kilopascal you can write kilonewton per meter square into kg cancel. It is meter cube and this is meter. So kilonewton meter is kilojoule. What has been asked in kilojoule? Okay, so the answer is 42.717 kilojoule. So this is good question. Uh, So now how can we calculate it? Okay, so from column M we cannot directly measure or get to column N, but using column N we can arrive at some point of time to like some quantity so that we can see. Okay, so the quantities used here is enthalpy and Helmholtz function. So firstly, what is Helmholtz function? Let here it has been denoted using psi. I am using it f as Helmholtz function. Okay, f is equal to u minus ts. This is Helmholtz function, and one is h minus ts. That is Gibbs function. Okay, so f is Helmholtz function here. Okay, now so let's see. I don't know about anything. Let's proceed and try to get to result. Okay, I have to calculate del psi by del v here as given and del psi by del t. Okay, no, see. So means del f by del v and del f by del t. So if I take this differentiation on both sides, d of u minus ts. So what we'll get? D of u minus d of ts. So here we will use product rule. T constant, differentiation of S entropy, S constant, differentiation of T. Okay, now see here, are we getting anywhere volume here because we have to like calculate del F by del V also, but volume is not coming. Okay, so how we can use get uh, get the volume term? See, here we are seeing TDS. So TDS relation, you know, TDS is equal to du plus PdV. Okay, so use this relation here, du minus du plus PdV. Okay, minus SDT. So du will be cancelled and this minus will make this both the term minus. So df is equal to minus pdv minus sdt. So now what has been asked? So del f by del v. So df by dv df by dv at constant temperature. This means this we have to find. So at constant temperature what it will become? Df by dv, this will be 0, right? If I simplify this, let me write it like this. So for temperature constant we can write equation 1 as Tf is equal to minus PdV, and for volume constant we can write it like this: Df is equal to minus SdT. So del F by del V at constant temperature is equal to minus P. This is another GATE-XE question, that if we take Helmholtz function as y-axis and volume on x-axis, so for a given isotherm, what will be the slope? So this will be the slope minus P. So P is actually the absolute pressure, right? So it cannot be uh, uh, less than 0. It will always be positive, but minus is there, so that's why it is non-zero, negative, and other things we will see in the next question. And here del f by del t will become v constant, will get minus s. So using these two we'll know. See, del f by del v at constant temperature will be equal to see, del f by del v at constant temperature will be equal to what? Minus p. So n1 is matching to m2 and del f by del t minus s. So minus is there, minus is not here, so minus should be here. So this is matching to n4 and n3 is matching to n4. Okay, now the next things. Next is about enthalpy and pressure, something related to enthalpy. So we should get some relation for enthalpy also. So if I use this relation, TDS is equal to du plus PdV. Okay, but enthalpy is not there. So how I can invoke? I invoke this relation H is equal to U plus PV. Okay, I simply know this. So U is equal to H minus PV. So I will use U here, H minus PV. So TDS is equal to DH minus D of PV. You already know what is going to happen. Some terms will be cancelled out. So using product rule, this will be PdV minus, sorry, plus VdP, right? Plus PdV. So this will become, so this will be cancelled out to this dH minus VdP. Now see what I have to calculate: del H by del P and del H by del S. Okay, so entropy cost. So I can write this as dH is equal to TdS plus VdP, right? So entropy constant here and pressure constant here. So this will become 0 in this case. Del H by del P will give V at constant entropy, and del H by del S at constant pressure will give temperature. So so N5 will be matched to M1. and N8 will be matched to temperature. Okay, this is it. So M1, M2, M3, M4, N5, and, and, and 148. Okay, this is the answer. So this question is from an steady flow analysis that I have already sent 2-3 questions from unsteady flow uh, prior to 10 days or 11 days before the exam. So this is very similar to that question. So what is given? A rigid insulated tank. Rigid means work done by control volume is equal to 0. Insulated means Q will be 0. Now containing ideal gas we can use H equal to CPDT or ideal gas equation. One bar is being filled from external pressurized line supplying the same gas at temperature is same but pressure will be different. That only then when the valve is removed, then due to this pressure differential that air will be filled in the tank. When the mass of the flow gas inside the tank has doubled, its temperature is. So what will happen to temperature? Okay, if mass has been doubled, mass is doubled. Okay, so let's solve this question. So this is the case. We have supply line pressure is, let's say, 300 Kelvin Ts, and Ps is 10 bar. Okay, and we have tank here. This is insulated, and here initial temperature is like at condition 1, initial tank condition, and P1 is 1 bar, and M2 is equal to 2M when this is given. So like at condition 2. So here we have to be very careful with the notation. So I is inlet, E is exit, and 1 is for initial condition of tank, and 2 is final condition of tank. Now why I have used these notations? Because there are only two equations that will help you solve the problems related to unsteady process. So here only exit is there. So I is there, no exit. So exit term or exit properties will become 0. Okay. One is initial condition and two is final condition of the tank. Now let's solve the problem. So there are two equations. One is law of conservation of mass, and second one is law of conservation of energy. Only using these two equations one can solve the problem. Okay, so from the law of conservation of energy, if I write final condition minus initial condition in the tank is equal to m inlet minus m at exit. Okay, so using this we can write, see here exit is, no exit is there, only inlet of air is there, so this will be 0, and m inlet we can write it as m2 minus m1. Okay, now the second thing is law of conservation of energy. Law of conservation of energy will be u2 minus u1. This is very reduced form because we have neglected the kinetic energy and potential energy. The whole expression we will see in class. So mihi plus q minus mehe plus w by the control volume. This is 0. Insulated. This is 0. Work done because rigid. No exit because only inlet is there. So we can write it U2 ideal gas. So we'll write it like small u1 mi. Just for ideal gas we can write CPTI. So now this we can write m u2 is uh, u2 we can write, sorry, here we cannot write it like this because mass is not same in both the cases. So I will remove this. Okay, now this will be m2 u2 minus m1 u1. Okay, now what we can do, we can further simplify. We can write u equal to cvt, so that will become t2 minus uh, m1 t1 is equal to mi cpti. Okay, now here we can use ideal gas equation pv equal to mrt. So m we can write pv by rt, and mt we can write pv by r. So here mt we can, what we can write, mt as p2 v2 by r. Okay, and here v1 and v2 are same, so I will directly write it like this. v1 v2 is equal to same since rigid container. So I will write it like p2 by r minus p1 v by r. Hence I will move this cv to right hand side. So cp by cv will be gamma. Okay, and gamma value we can take as 1.4 here as given. Now we can write it like p2 minus p1. One more thing, simultaneously what we can do here, see, from the first equation we got mi as m2 minus m1. So m2 minus m1, so m is this, m2 minus m1 times of cp ti. m2 minus m1 will become, m is pv by rt. Okay, so p2 v by rt2 minus p1 v by rt1 into cp into ti. So here if I divide by r by v here, so it will become p2 t2 minus p1 t1 into cp into pi. So here in this equation we don't know the final temperature T2. Okay, and we don't know the pressure because P2 minus P1 is 100 kilopascal. 1 bar means 100 kilopascal. P2 by T2 minus P1 by T1. P1 is 100. Initial condition of tank and initial temperature 100 Kelvin. This is uh, Cp by Cv will become gamma. This would be gamma 1.4. Inlet temperature is 300 Kelvin. Okay, so this is our first equation. Now we should know about P2 or T2 or ratio of these two. Okay, so we can use ideal gas equation P1 V equal to MRT1 M1R1 T1 P2 V M2R2 T2. Okay, so R cancel, V cancel, and here we know M2 equal to 2 M1. Thus we need to find out P2 by T1 is equal to M1 by M2 into P2 by P1. Okay, T2 is equal to T1 times this M1 divided by 2 M1 into P2 is pressure. Finally, we don't know P2, and P1 is 100, so that will be 3 by 2 times of P2. So P2 we can write 2 by 3 times of T2, and this ratio P2 by T2 will be equal to 2 by 3. So use this and this in equation 1. What we'll get? We have from this equation, see, we can write P2 as 2 by 3 times of T2 minus 100 is equal to P2 by T2 is, we can directly write 1.4 into 300, and if we solve this, T2 is only unknown, it will come out around 360 Kelvin. So in steady flow problems, we have to concentrate only on some two things. First one is law of conservation of mass and then energy. Those equations are sufficient.